Hello and welcome to our video presentation. I am an AI-generated voice speaking on behalf of the authors of this research, Ikko Yamane, Yann Chevaleyre, Takashi Ishida, and Florian Yger. In this presentation, we are going to present our work, Mediated Uncoupled Learning and Validation with Bregman Divergences, Loss Family with Maximal Generality. In Mediated Uncoupled Learning, or MU learning, the goal is to estimate the conditional expectation of y given x here. Y is the output variable and x is the input variable. However, we are not given xy pairs but only xu pairs and uy pairs for training with another mediating variable u. In this framework, we don't need to collect xy data jointly. Because of that, we cannot directly perform supervised learning methods. Note that classification can be handled by one-hot encoding the class label y. Here are some examples of MU learning. The first example is translation between minor languages, in which we want to translate between two minor languages, but we don't have data of direct translations between them for training. Instead, we have pairs and input data x in the first minor language and its corresponding translation u in the major language. We also have pairs of text u' in the major language and its corresponding translation y' in the minor language. The second example is low-quality image classification, in which we want to classify low-quality images x since it may be difficult for a human labeler to recognize a low-quality image when collecting training data. We use a high-quality version of the same image u', and we ask the labeler to provide the class label y' for that high-quality version. The third example is counterfactual prediction, in which we want to infer the counterfactual data y, corresponding to a factual data x input that we have. It is impossible to observe the factual data x and the counterfactual data y at the same time, but we may observe some variable u with each of them. Existing MU learning research only focused on the squared loss. A natural question is, can we handle other loss function? In particular, for classification tasks, the cross-entropy loss is more popular. We want to extend MU learning to allow for a more general loss function family. To what extent can we generalize the loss? These are the motivation for this work. To formalize the general MU learning setup, we write down the assumption we make. The first assumption states that the conditional expectation is the unique minimizer of the expected loss. The second one is that the loss is non-negative. The third one is that the second-order derivative taken with respect to the first and the second argument exists, and it is continuous. Banerjee et al. Showed that these conditions imply that the loss has to be a Bregman divergence. A Bregman divergence is defined as in this equation for some convex and differentiable function. Bregman divergences are a wide loss family that includes the squared loss, the cross-entropy loss, and so on. Conversely, all Bregman divergences satisfy assumption 1 and 2 under assumption 3. Motivated by this fact, our goal now is to develop general MU learning methods for Bregman divergences. Here is our first proposed method called two-step Breg-MU. Note that the order of the arguments cannot be reversed in general because Bregman divergences are not necessarily symmetric. This two-step method gives a statistically consistent estimator given correctly specified models H and F. However, our theory requires the loss function to satisfy some conditions to be verified. To overcome this weakness, we also propose a one-step method called joint Breg-MU. The objective function of this method asymptotically upper bounds the ordinary supervised loss, E, L, Y, F, X. This method introduces some bias but encourages smaller variance. Our analysis shows that the excess risk of the prediction given by joint Breg-MU is bounded by a vanishing error term plus the multiplicative bias term. This suggests that the bias will be smaller if either of the two factors is small. In the last two conditions at the bottom of the slides, there are similar quantities to the bias factors interestingly. We require them to be positive in order to obtain the rate of the vanishing error. This might mean that having a positive bias is helpful for the convergence. Note that those conditions can be easily satisfied by adding small noise to the variables. Using a similar technique to that of joint Breg-MU, we can obtain an interval containing the validation loss. This interval is useful because it holds for any functions, f, and h, and uses only xu data and uy data. We tested our methods in low-quality image classification. In this experiment, the task is to predict a class label Y of a low-quality image X. However, because of the low quality of images, labeling process in the training data collection can be difficult. This labeling process can be made easier for higher quality images. We assume that we already have labeled higher quality images and pairs of low quality and higher quality images. We compare the proposed methods two-step Breg-MU and joint Breg-MU with three existing methods, naive, two-step double-R, joint double-R. To have an idea about how difficult classifying low-quality images is, we also showed the result for training given access to ordinary supervised data. From the results, we can see that joint Breg-MU showed the best performance, and the performance is not too far from the ordinary supervised learning. We also tested the proposed validation loss interval estimator. In this example, X is a uniform random variable, U is a noisy cubic function of X, and Y is a noisy quadratic function of U. The blue circle points are the true validation losses of the proposed method, and the blue solid bar are the proposed interval estimates. The orange triangle points are the true validation losses of the existing method, and the orange dotted bar are the interval estimates derived by the existing approach. We can see that the proposed intervals are narrower but still contain the true points. The difference is especially clear for the larger sample size. To sum up, this work proposed MU learning methods that can handle any Bregman divergence-based loss function. This overcomes the previous limitation of MU learning. For future work, we are interested in the analysis of the strongly convex case. Cases in which the goal is not to estimate the conditional expectation are outside of the framework of Bregman divergences. It would be interesting to study such cases. That is all. Thank you for watching our video.